All right. Hi, everybody. Evan here with the last part of Homework 5, where we will be deriving a mesh calculation column. Okay, so a mesh column, distillation column is basically just a regular distillation column. Is how you would how every um graduate level or doctor level, the person that has a in-depth information about distillation column would construct a distillation column. So they would just basically code out and calculate how we would run this a message selection column with the given parameters that we were given. Okay. And I just want to make note what a mesh is. So message selection column, the variables, it just stands for material or flow rate balance equation. So the M stands for material or flow rate balance equation, both components of total. E stands for equilibrium equations, including the bubble point and dew point equations. S stands for summations or stoichiometrics equations or composition constraints. And the H stands for heat or enthalpy of energy balance equations. Okay. All right. And what we are asked to do, so first we're given parameters here, which I'll go over when we talk about initial conditions. Um, but for this initial conditions, for this, you're basically supposed to first, derive a messy distillation equation for the first stage below the condenser, reboiler, and all the stages in below, assuming any stage can be the feed stage. Um, Using this, so first we'll actually take first do a material energy balance. Not well, we'll first make equations for our liquid vapor and temperature gas flows going into the distillation column, and then kind of make guesses. So you know how we in our previous videos before we've had guesses for what these temperatures would be, and then we run into our solver. It's kind of what we'll do now. So we'll first have our equations for our liquid flow and vapor flow for the rectifying and stripping sections, and reboiler, of course, for the liquid flow. And then we would code out guesses for these respectively in a matrix C. So we would make guesses throughout for the first stage below the condenser, the reboiler, and then the stages and all the stages in between, so the stripping and rectifying stages. And then from these guesses, we will implement the mesh equation in code, solving Newton's method, applying Thomas algorithm, and linearizing tridiagonal block equations at each Newton iteration. Okay. And from our coded out derived guesses that we have, we will then use our tridiagonal Thomas algorithm equations that we did actually in the last video to kind of work backwards from basically using our e's and our solved was tridiagonal matrices that we have for our guesses to then rework to find our desired flow rates, as you say. So yeah, well, compositions. So temperature, I mean, our compositions for temperature and the flow rates we have. So yeah, that's kind of how we will work this out. And then I also want to mention that most of these references, so we can start with the code. So that we can start with the code. For a code, we of course start with our GitHub, have our libraries that we imported that we kind of use throughout. So three big codes that we can actually replicate from this. So I was able to do the initial well, we were started to give out initial we were given the initial layout to what we need to have our background for the mesh equation. So a lot of these come from our previous videos that we worked with. So I know a lot of this comes from our Ponchon Savarit homework code that we did. We talked about the NRTL and ideal situations for a distillation column. Our tridiagonal matrices that we really just did for part A, which I just said we'll go over later on when we um, do later for our mesh equations. And also this dynamic distillation column. So we also be using our um Jesus, I can't talk. Our dynamic distillation column, kind of for the unknowns that we have, how we will lay that out as well. So this is where a lot of this comes from. These three, and a little bit from other homework that we did in the previous videos. But yeah, let's get started. So kind of like I said, we have these equations here. We'll be using for our props ethanol and water. And then we'll be using our gamma ideal, our dew point ideal, bubble point ideal, and Oh, actually, no, not that. I'm sorry, but we'll be using the NRTL, like I just said earlier. Referencing this from our contrast cyber because we'll be in the Jacobian region, which we need to be in the NRTL. We need to be in NRTL. We use NRTL for our dew point, bubble point for our Jacobian. Okay, so we have that. Word from our last equation, a dew point, double points, a dew point and bubble point for to find our temperatures and then our XY compositions, which we'll be using actually our flash ideal, which we didn't really cover for our homeworks. We did in class, but basically what we'll be plugging in are our information that we gathered from our dew points and bubble points using an NRTL and the dew point from the ideality and plugging them into our flashpoint to then give us our X, Y, and our vapor feed compositions for our mesh calculations. So now to our initial values. We have our number of components, which just come from we actually use this NP our molecular weight dot size, which actually allows us to it basically calculates what the molecular weight would be for the components, and from that it gives us basically what are the number of components we're using in this distillation column, which is kind of interesting. Of course, it's just two because we're only using ethanol water. But if we added any extra components into our distillation, it would use the size, and then from the size, it would gather how many components it would be. So it's pretty interesting. Um, Next is our is it feed total? I think what is it? Yeah, I think this is our feed, our flow, a feed flow. Yeah. Okay. Our feed flow. Actually, no, it's not our feed flow. It is our feed total. Yeah, our feed flow. We have our compositions for the respective um for the respective I can't talk, our compositions for the ethanol and water. We have our pressure, which is at 100,000 pascals. Our dew temperature and our bubble temperature coming from our bubble dew temperature in RTL and our bubble temperature from NRTL up above. Have our feed temperature, which is just our average of the bubble temperature plus the dew temperature divided by 2, so the average. Then we have our liquid and vapor compositions and also the vapor feed coming into the distillation column. We're getting that from our flash and RTL, like I said earlier. Then we have our feed enthalpy. Okay, so of course, um, like I said earlier, when I'm referencing the mesh calculation, the H stands for enthalpy, so heat. And for our heat, for the equation, so we have to also calculate enthalpy for our mesh calculation. Okay. And then for our initial conditions, it's kind of based on our DOF. If you remember, we did our DOF calculations. I think it was homework 4, homework 3. But for the requirements, we're basically listing that one is how much coming from our distillate, coming out of our distillate. So we have 1 mole per, I think, second coming out of our distillate. We also calculate our bottoms, so we know our bottoms is equal to our feed, our total feed coming into the distillation column minus our distillate coming down from our distillation, and the distillate coming down. So we were able to calculate the bottoms total. Okay. We have our reflux, which we know is 5 from our prompt. We have the number of stages, so NS, so number of stages as 10, and then the number what is it? I guess it's the number, what is it? The feed ethanol water at the 8th stage, counting from the top. I think it's the number where the feed enters, so it would be entering at the eighth. Yeah, so at the eighth, so this is where the feed will enter at NF. So the feed will enter at the 8th stage, kind of from the top at the destination column. Okay. So now let's get started. First, kind of like I said earlier when we started off, we want to first get our liquid, kind of have equations for our liquid, our total amount of liquid and vapor and temperatures for our guesses, kind of, where we would then plug them into our unknowns. We'll be using unknown zeros and then filling them out later with the information. So Well, basically, we'll need to make equations for our initial gases for our total liquid, total vapor, and then our T gases, and then using unknown variables. We're using a matrices for this, but basically using a matrices to then kind of combine both of the guesses and the unknown matrices that we have to basically have. I'll explain later while we go through it. But let's get our equations for our unknowns. I mean, for our guesses. So we do our initial guesses, and then we'll do liquid first. So we can start with the rectifying stage. So this would be L total of rectifying. And this would be equal to, what is it? What is it? R plus D. Yeah, so it's our reflux plus our distillate. Okay. And then our L total for the what? For the stripping section. This is equal to, I'm trying to remember. So it's the also the feed coming down. So it's the liquid total already coming down from the rectifying section. Um, plus our feed coming in from our F total coming in from the feed. So this will be multiplied by 1 minus our vapor feed composition coming in from our feed. So this will give us our liquid. So 1 minus our vapor feed composition for will be give us our liquid feed composition. So we multiply that by the total amount of feed coming in. Okay. Next we will have our vapor stages. And I'm actually just copy and paste both of these because they're kind of similar. I just change it. And then this will just be our distillate plus R plus 1. And then this will just now be, okay. And the last thing I forgot to ask on the liquid stage, I keep doing every time I practice this, is our reboiler. So we have to do something for our reboiler, which will be, how can I name this? Um, well, I know that we'll be using MP space for this. And from MP space, we'll be taking, what is it? The last variable, of course, from our status. So this will be, trying to remember. This would be the dew point, the dew temperature. Oh, bubble temperature first. Bubble T. Oh no, that's for our temperatures. For our, and that's when we use MP1 space. For our, I'm gonna come back to that because I have to remember real quick. But for our temperatures, our temperature gas, T gas, I know this will just be should be equal to MP1 space. First our bubble temperature at NRTL, and we'll be using the vapor composition, respective pressure, and we want the last component. Oh no, we want the first component because you remember, when we plot out our bubble T at NRTL, we know that it gives us our temperature and also our composition. So it gives us two it returns us with two numbers, which will be only our temperature. So we'll be only pulling the first first temperature, the first value, which would be our temperatures. And we'll also do the dew temperature, dew T at NRTL with respect to X, and also our pressure again. And we're pulling our first value as well. Okay. This is our T gas, so I need to also copy this. Thought I had this. Did I delete it? I guess I deleted it on accident. Oh well. I'll just rewrite this. This will be vapor now. And then, okay. I'm trying to remember. It's blinking right now. Hmm. What we did for the reboiler. Because the reboiler, what is it? Oh, this is really easy. Why am I blinking? It should just be L tote from the stripping minus our bottoms leading. Yeah. I don't know why I didn't think about it. Yeah. That should be right. And then we can just call this um L tote or bottoms. Okay. This should be right. Um Let me check real quick just to make sure it's right, and then I'll be right back. Okay, so I just checked. I'm sorry. We did not need this. I'm just thinking far ahead. When we do our unknowns, we have to separate the stripping section and the condenser, I mean the reboiler. When we plot out our unknowns when we do set our matrix C. So we don't need that. I'm sorry. But I do want to change this to multiplication. So it's actually a reflex times or distillate, which I should know because we've done this multiple times. But yeah, it's reflex times our distillate gives us our liquid total of our rectifying. And the reason why we get um this section here, our D plus R plus one, is because we end up with D, our distillate times our rectifying plus our distillate again. Um, which we know we can substitute out the D, so we get D plus, R plus one. So that's the reason why we get that. But yeah. Um, I can just leave it as this as well. So I may just do that. Yeah, yours. Make sure this is right. But um actually I'm leaning to R plus one. I like the depth one. Okay. Anyways, yeah, this is our initial guesses. And now we will do our notes. So we'll make a matrix C. 5 by 10 matrix C. Um, so unknowns is equal to NP dot zeros. And this will be comprised of, so we do a 10 by 5. So we do from the number amount of stages that we have. So we have 10 stages. So it'd be from NS, and then we will have the components. So we multiplying from our components, but we went it by 10 by 5. So we'll do NC, because we know that's our components, we know that's 2 times, excuse me, times 2. Oh, excuse me again. I don't know what's happening. Plus 1. So this gives our 10 by 5, and we can just check here. We do unknown dot shape, shift enter. Oh, you get to do double parentheses here. Yeah, shift enter. Yep, 10 by 5. Perfect. All right. So now we can start again. So we can do, what is it? Yeah, so we do again our liquid phases where we will do it is unknown. And from this, basically we'll have 10 rows of 5. So all 10 rows have 2 stages, 2 grabbing our liquid compositions, and then 2 grabbing our vapor compositions. And the last one, the fifth one, be grabbing our temperatures. Okay. So what we'll do is that we want to grab everything before and our NC. So we do everything to our, what is it? Our NS. So that makes it to 10. So we'll grab everything before 10. So we get from 0 to 8 for our major seed, 0 to 8. But we get from stage 1 to stage 9, stop at 10, and that's where we grab. And then we want this from NC We want everything before two, so we want 0 and 1. So we want we want everything before 0 and 1. Okay. And this will just be, we'll do our liquid total of the rectifying, and we'll just multiply this by our liquid composition. So X, and then this will be the exact same too. This will just change is that, what is it? Was that be stripping now? We'll be grabbing the Y compositions, multiplying by the Y compositions, the vapor compositions, and then we switch this out, and this will now be from ends S on. I'm pretty sure. No, I switched them. Yes. So this is supposed to be NC here. Yes. So we're grabbing two competitions. So we're grabbing the two Lego competitions, two Lego competitions. So then this is now from the next two Lego competitions. So it'll be from, yes. And then we'll be grabbing ending right at before the last column of our 5 by 10. So we are ending right at the fourth column before we get the fifth column, because the fifth column will be our temperatures. Correct. Yes. All right. And then we had to do a reboiler. That's what it was. So then we had to do the reboiler, which would be our last compositions. Yeah, and this still be from, let's stop at the ninth position. And this would be what is it? Liquid totals, stripping, it should be B totals times our liquid. Yeah, times our liquid composition. Okay. All right. Next we do our vapor. Which we can just copy and paste these now. And they'll be the same thing, but just changing out. Okay. And everything else I think stays the same in here. Oh, let's put C here. There we go. All right. And then we have next our T gases. So our temperature, which this would just be unknown of, what do we put here? I guess this would be our last, be -1. And then this would just be what, our T gas, I'm pretty sure. Yeah. Shift enter, cannot broadcast a 2 by 5. Cannot broadcast input from a 2 0 into a shape of 2 by 5. Did I do this wrong? Let me switch these out. You see, it was just NC because I guess it's the first two. Cannot broadcast 2 to a shape of 5, 2. I got issues with this. I thought this is correct. Interesting. Did I have it right the first time then? I think so. Maybe. Let's try it. Let's switch these out. See if it was like this. I think that was actually the problem. Oh wow. Okay. I think I was right then. I think I was right the first time. Should I trust my instincts? Okay. I think this has to be switched now. This would be NS, what, NS, a -1. What is it? It's 9.5, no. I need to be 10.5. Yeah, I think it should be 10.5. I thought you still put the NS here. Is it before? That would make sense then. Hmm. Okay. I'm gonna check out this reboiler stage. I think everything else is correct now. I think I had everything else right. I think I just gotta recheck the reboiler stage and then we should be good. Okay. Okay. We got it now. We got it now. Okay, so I was on the right path. It needs to be the eighth because now this makes it 10. Makes this 10 by 5, but we need it to be 8 by 5 because we're doing intervals of 2. So yeah, it should be F. So we're using F here, not S. I'm sorry. F. And then this needs to be C. That's why it wasn't working because I had S here. So it's going to 10, which that's impossible because you can't go to 10. Um, so yes, this needs to be F. So we have it to the eighth. Gotta have it at 8 instead of just 10. Okay. And then this needs to be all the way to the end, which makes sense because our temperatures are our last intervals, and then it needs to be the last TS. So yeah, now um this should work. Can I broadcast it array? Um oh. Hmm. Needs to be grabbing the 10 to 5. So it needs to grab the last input from this. Not 10 4. Um what's 5 here? I use R. No, I cannot use R. Okay. I mean, that would work actually. But mm. Okay, so first guys, I'm sorry. There's a lot actually I looked back to all my stuff and there was actually a few mistakes. So I wanted just to kind of restart for our unknowns that we have and kind of rework back what we have. Starting from our initial guesses because there's some stuff that I missed as well, which then affected our unknowns when we were trying to create our shape for our matrix. So I'm gonna try to go back and then fix my errors and we can restart with the unknowns. Again, sorry. I know it's gonna be kind of a longer video because of this mistakes. I may make a few more mistakes in the next part. So hopefully not that much, but we will get through it. Okay. First, we go through our initial guesses. Of course, we start with our liquid stages. The stages coming from our condenser to until we get to our feed. Well, this is actually relying on all the stages below the condenser from the rectifying stages to the stripping stages, not including the condenser in the reboiler. So if we do for the total liquid feeds for our rectifying stage, we know that is the reflux times the distillate, and this is coming from the condenser. So we know that from the reflux times the distillate, we will get a liquid flow coming down. That was recycling back into this distillation column. Okay. From there we have our liquid total of the stripping, which um we also know that this for our liquid is be the total liquid coming down from the rectifying stage, plus the liquid feed coming from the feed stage, times one minus our vapor feed. Okay. So this is just our no, the one minus the vapor feed is basically kind of like the quality. So we know that this would be we have vapor composition coming in. So if you want the liquid, we do one minus the vapor composition and then multiply that by our feed total. Okay. All right. Next we have our vapor stages. First again for the rectifying stripping stages. We know that here, and this is our my first mistake. We initially, and I explained this as well. I don't know why I should just leave, but we have our rectifying times our distillate plus our distillate again. And if we want to, you know, simplify this, this would literally just be R R plus one, factoring out the distillate from the equation times our distillate again. So this is what it would actually be not plus distillate. I made a mistake in the past. I mean previously. So this is what our actual equation should be, R plus one times distillate. But we can leave it in the other form too as well, and that also be fine. And then we have our vapor of the stripping section, which is the vapor totally of the rectifying, and this should be minus. So it is minus our feed of the total, the feed coming in minus our vapor. And this is because we are going against the distillation column. So of course, distillation column, yeah, majority of it's coming from the liquid. And then the liquid gets reboiled back up from the reboiler and then comes going to a vapor stage. Okay. And now we have the vapor coming from the rectifying stage is opposing the liquid because of course that's the vapor is all coming from the stripping section is not coming from the rectifying stage. So it's kind of inverse. But yeah, and be subtracting from the feed. That's why we put mine instead of plus, because we're not adding, we're kind of subtracting, if that kind of makes sense. And then the T-gas, this is actually fine. This looks the same, but the only thing I do need to add, for our MP lens space, we need to also add a third condition, which would be how many uh this would be for our unknowns for our matrices, but how many temperatures are we collecting for this? And we need to collect 10 because we have 10 stages. So we do NS for in stages. Okay. So that's the last of it for our initial caches. That should be all the fixes. Again, I'm sorry for the mistakes and the mistakes previously. Let's keep going. So we have our MP shapes, our MP zeros, okay, and we'll be filling those out as we go, of course, for our matrices, and we have a shape of 10 by 5. Okay. So we reprint out our shape 10 by 5. Now, I want to explain this furthermore so it makes more sense. So, our 10, of course, represents our 10 stages. We have our top is our condenser, bottom is our reboiler. The 8 in between is our stripping and rectifying stages. Okay. Now, the way we will be splitting our rectifying stages is from, of course, our feed. So, we know where our feed will be. We know where our feed will be because we already listed down it'll be on the 8th stage, and it gives us in our in our question in our questions it gives us where our feed will be at. Okay, so if we start by this, we kind of go back to what we were saying before. We do our liquid and then we do unknowns for the stripping section. We know that we want our feed for the stripping, of course, so this would be equal to the liquid total of the stripping. We have the rectifying, I'm sorry, of the rectifying, and we'll multiply this by our vapor composition. Okay. Now, we know that we want this from the beginning of our stages, so from stage 0 all the way to stage 7 for Python. So from stage 1 all the way to stage stage eight. Okay, because from stage eight, that's when the feed comes in, and that's when we switch from rectifying to stripping. So what we want to do is that we will do our I forgot what this is, colon. Yeah, our colons. I'm pretty sure it's a colon. Yes, and then we'll do it all the way to our feeds. Right, our feed stage. So this is why we do colon NF. So this will capture all the stages before we reach the stage as we reach the stage eight, which then it will cut off. Okay. And then we want to capture this by every two lines. So we have, of course, it's 10 by 5. We have 10 rows and 5 columns. Okay. The 5 columns capture one, they capturing two, it's kind of like 2 2 1. Okay. So it's capturing the what is it? Is it the vapor composition vapor? No, it's capturing, I'm pretty sure it's actually the vapor compositions, the vapor liquid compositions of, yeah, it's okay. Is it the vapor liquid compositions or is it trying to make sure this is correct. Yeah, I'm pretty sure it's the two liquid compositions and two vapor compositions for the respective compositions. So for ethanol or water we have, so it's the two liquid compositions, two vapor compositions, respected to the either rectifying shipping stage for liquid and vapor. So yeah, we have our liquid compositions for ethanol. Yes, yes. So we have our liquid compositions for the ethanol and water that you can capture in the two groups, and then next to will be our vapor compositions of the liquid and water, and then we will have our temperatures respective to each stage. Okay, and we will split that from our liquid rectifying and our stripping section rectifying, and of course our vapor rectifying and our vapor stripping. Okay. All right, I'm pretty sure I got that right. But then we want this basically to do the same thing like this. We want to capture everything of all the rows until we get to our second column. So NC. Okay. And that's what I was trying to do earlier, and I just totally messed up on. So we can copy and paste this. And now the next switch is that, of course, if we go to our stripping section now, we will first need to multiply this by our liquid compositions now. And we will need to change this now that we want to capture all the stages below our feed now. So it'll be from our feed to actually um before our reboiler. Okay, because for our liquid, like I kind of mentioned earlier, we want to capture everything before our reboiler because our reboiler has its own stage as well. So what we do here is that we would do everything from the feed to the reboiler. So it'll be NF colon to -1. -1 is capturing our last point, our last column, the column 10 in this case. So we're stopping at column 10 before we get to reboiler because reboiler is that 10, the 10 row, 10th row. Okay. And of course it'd be the same as well. We're capturing 2 by 2. Okay. And this would be for stripping. And then we need one for the bottom, I mean for the reboiler. Okay. So the reboiler would just be -1 because that'll be our last, that's the last row. And then it'll be, of course, still and C. All right. And here this will be our bottom. So B total times our vapor composition. Yes. Our vapor composition. Excuse me. All right. So this is our liquid phases. Okay. I'm highly certain this is correct now. Of course I'm gonna double check it as well when I'm done with this, but I'm pretty sure this is way more accurate than we have. We can check as well when we actually I can check now. So we wanna I can check the numbers we have now. Let me shift enter. Incomplete. Oh, I got scared me a little bit. So we check now. This is correct. Okay. I know these numbers. Yes, these numbers correlate. These numbers do correlate. All right. So we have it now correct. Yes, we have everything before we get to our last column. And then, yep, perfect. Okay. Next we go to our paper, which we can actually now copy and paste. These stay the same except for this one. We don't need that anymore. We can actually just capture everything from the feed. We don't need to worry about the reboiler in this case. Um, and these are, I think, are the actually the size of vapor. And let me check. I made this. Oh, I made a switch to compositions. Oh, that's why. I'm sorry. We do have to make a change to this, because it's kind of just capturing only the first two columns, but now we need to capture column three and column four for the paper phases. So what we need to do is that we will start from our second stage, our second column, and we will go to our last point here. Oh, I don't think I'm on number lock. But then we will go to our last point on the column. So we will end. So we will capture our third and fourth column here on Python, be two and three, and we will stop when we get to our last column here because this is for our temperatures. Okay, so this is what it should look like now, and it should update now once I do this. So shift enter, perfect. We got it. We got it. We got it. Okay, now we have our captured temperatures. I mean, captured phases for liquid and vapor are respected for all the stages that we have. So now the last thing we need to fill out is our last column, which is our temperatures at each column. So we need to do our T gas, temperature gas. Okay, which this should work now. If we do, we want to capture all the rows, so we can just use a colon and capture everything for all the rows, all the stages, and then we would just do to -1 to capture the last column that we have. Okay, and this is just equal to our T gas. Now we have up here. Okay, so we shift enter. Oh yeah, we have it now. Okay, so now we have a 5 by 10, a 10 by 5 matrix of our basically kind of our guesses that we want to put into our solver later to then try to find our actual numbers for our distillation column. This is kind of like I said, our guesses that we have for each of the stages in our for our distillation column. Okay, so now we will then actually get into our questions, which is I'm gonna of course check the numbers again. If we have any things that we need to update, I will fix these. But we will now get into our first part is which is deriving the equations for the first stages below, the condenser, the reboiler, and all the stages in between. Okay. Okay, so before we get started, I did just do a double check, and there was one small error. I didn't make this liquid compositions that were multiplying the bottoms by not vapor compositions. And that makes sense since liquid compositions is the flow leaving the reboiler. I should have thought about that, but yeah, it's the liquid compositions multiply that, and then the numbers I checked the numbers and they do match to what I have, so we are good here. All right, so now let's move to our first part of the homework. Oh my gosh, I just blanked out. Sorry, it's late. Deriving the mesh distillation equations for the first stage below the condenser, the reboiler, and all the stages in between. So what the equations that we're looking for are mass balance, not energy balance, but a mass balance, a well, I just blank out. What is it? Is it energy balance? No, it's a enthalpy balance, a mass balance, enthalpy balance, and a I know what they are. I just it's blanking right now. It's EB. So if I write them down, they would be our mass balance, our enthalpy balance. We state as EB, and then we have another one that's EQ. That I have listed down. Wow, EQ for It's not energy balance. Okay, so before we start, I checked my numbers and there's one mistake before we start the first part of our homework. Finally. But it's actually the reboiler part. It's just a tiny error which I should have caught. But when we do the liquid phases, we need to multiply by our liquid composition since liquid is coming down into a reboiler before it gets heated up to vapor. So we shouldn't be multiplying the bottoms flow rate by vapor because there's no vapor coming leaving the bottoms. It's just liquid. So it needs to be by X composition, which then matches our numbers and from my reference sheet that I practice with. So this is correct now. I should have caught that before, but I just didn't. So now we're good now. We are good now. So now we will start with the deriving of the mass distillation equation for the first stages below. The condenser, the reboiler, and all the stages in between. So the stripping and rectifying stages. Okay. And the three equations that we're looking for are a mass balance, our mass balance, our equilibrium relationship, and our enthalpy balance. Okay. So we can start first with our first stage below the condenser. Okay, so we define this by on the stage one is our first stage below the condenser. And we'll be using vector, so vector representing the so we're doing the vectors from our current stage, um, which will represent the column that we're working with. So the vector of our first column, so the vector of a current stage we're working with, and the vector, and we'll call it vector 2 for the vector of the stage below that we're working with. And then just for a heads up, the vector 1 would be the vector above the stage from our current stage. So we'll use vector 1 for the next definition we're worrying about. So you don't worry about that right now. But yeah, so we'll have vector 1 and vector 2 representing our columns here. Okay. And what we want to do is that we want to first start with our liquids. So we wanted to basically pull out our liquids and vapors that we have here for our unknown matrix C that we have. So we wanted to pull it for our liquids and vapors for our current stage, and then also our liquids and vapors in our second stage for our stage below, all the stages below our current stage. And then we want to also do this for the temperatures at our respective current stage and the temperatures at our stages below. Okay. So how we do this. Like I said, we want to split these, of course. So two the we're gonna split the two variables because we're capturing liquid and vapor. So we'll split these because we need to capture our liquid, which is in these two, and our vapor, which are these two. Okay. So we'll first do JMP because of course we're using Jacobian for this, so we need to use JMP. JMP split. Okay. And we will use vector because it's for our current state. And this will be we're actually be grabbing all of this until the last. So we're using from our first column all the way to something in our last column. Okay, so it'll be so grab all of the column besides the last one, so it'll be -1. And we're splitting this into two. Okay, so if we return this, we can return L and V, shift enter. And then if we use stage one, unknowns stay at 0 and unknown at 1. L2 is not defined. Yeah, we back this up. But we compare these, we will then see that we get what we are looking for. So for our liquids, we get that it matches for our first column. That gets our 2.819, and then our 2.18. And then we get our 3.38 for our vapor and our 2.61. Okay, so This is correct. And then we just have to do this for the rest of them. So we can just copy and paste for our liquid twos. And this we have to variable this vector two. And then this is actually all it is as well. And it will just be grabbing the next column here. So it'll be the same numbers because these are the same numbers for both these columns for right now. But they'll be grabbing the next column. So I'll be grabbing the liquids for the stage below our current stage. So our current stage, which theoretically, well, technically it'll be this stage because this is a condenser. So it's our current stage is stage one here, and then our stages below would be our stage three. Okay, theoretically, I mean technically, but anyways, you get the point. And then our temperatures. All we'll be doing is I will do equal to the vector that we're working with in the last. We'll be taking our last value from the last column, of course, and then move back to be the same thing, grabbing the last column for our temperature. And we can also check this as well. All right, shift enter, and you see we get our temperatures respective from what we're going for. Okay, so yeah, we work. So then from here, we also need to have our mole fractions. So we have our x mole fraction and our y mole fraction respective to the current state. So we need to also find that as well, which is kind of pretty simple. It's just the liquid from our current stage divided by NP sum of the liquid. And it's the NP sum of the liquid because if you remember, there's liquid for both the two components. So we need to have the sum of both of the two components, and then we're divided by the liquid that we're currently using for the volatile liquid. Okay. So that will be our liquid component. And then we do the same thing for the vapor. So vapor should be just be vapor divided by NP sum of the vapor. Okay. All right, and then for our equations, like I said earlier, we have mass balance, equilibrium relationship, and then we have our enthalpy balance. Okay. We can start with the equilibrium relationship. And the good thing about this, the equilibrium relationship will not change throughout. It actually will remain the same as we go on from the reboiler and all the stages in between, which is really nice. And actually, all we're doing for the equilibrium relationship, we already have this equation, but we are just kind of taking this bad boy right here. It's the same concept. Um, that we use for finding our bubble and dew points in NRTL. It's just our liquid composition times our gamma times our saturated pressure or vapor pressure, and we know that's equal to our vapor composition times our actual pressure. Okay, so let's just write that down now. So we have X times our, this would be P dot NRTL of gamma respect to liquid and temperatures. Um, what is it? Times our PVAP, back to temperature. And then this would be equal to, like I just said, our liquid times our liquid composition, I mean vapor composition times our pressure. But in this case, we want this equal to zero. So we will subtract this part here, and we can actually just equal this out, and we can try to you will get our equal molar relationship. So you see here, this would be our equal molar relationship. And this will we get into the next part, which is scaling. Okay, so I really don't know much about scaling. I know we did this in class. But basically, we want our scaling, our return to be in between the ranges of 1 to 0, closer to 0, more so. So what we would actually need to do in this case for all our equations that we will actually divide by our relative factor in this case, which is depending on the equation, before our equilibrium, our relative equilibrium, I mean For equilibrium. Well, for Raoult's law. For our Raoult's law. Let me just say that for our Raoult's law. We would divide by our pressure again. So by doing this, invalid syntax. Oh, divide by pressure again. As you see, our number is way closer to zero. So that's basically what we're doing. And we would do that for all molar balances, and it will have a different variable depending on the molar balance. And we will get into that. Okay. Depending on the equation. Sorry. But yeah, let's not do the mass balance. So mass balance, of course, we're doing it from our current stage. Um, yeah, from the stage below. So for our mass balance, we know that we have the liquid coming in, of course, from the condenser, which is our reflux times our distillate times our vapor composition. Okay. That's coming down in the liquid form into our stage. We also have the vapor from the stage below coming into our current stage, and then that's leaving our current stage is the uh, liquid at the current stage, then the vapor at the current stage. Okay, so this is our mass balance of the overall stage below the condenser, and we will be dividing this by our total feed. So dividing this by our feed total, our total feed of the distillation column. Okay, total flow of the distillation column. Um, yeah. Yeah, okay. Yeah, that's correct. And then for our equal molar balance, I mean enthalpy balance, all we would just do is now just multiply these terms by the enthalpy, uh, liquid enthalpy or vapor enthalpy. So for this variable here first, this is our liquid coming into the stage, so this would be I'll just put this in now, HL dot P dot HL and I'll just copy and paste this. And then it should be respect to, and now we have to also add our reflux temperature and this reflux temperature will be for this variable here, for the reflux coming down from the condenser. Okay, so we'll do reflux temperature. Um, then next add what? The vapor V2. Oh, my number lock. V2. We're coming from the. Oh, I forgot to put that here as well. Good thing I got that. The V2, so it'd be the vapor of the V2 and then T2 temperature coming from the stage below. And then it's minus the liquid enthalpy of the current stage and then the current temperature at this current stage and then also minus the vapor enthalpy of the current vapor flow, current vapor, and the current temperature, sorry. It's late at night. My brain's not processing as fast as I want it to be. And then we want to divide this by our what is it? Our feed enthalpy, which we have up here. Yep, right here. And we're also getting the total feed from right here. Whatever. And oh, I remember. I remember. Sorry to scare you. But I remember when I said something about it as well, that I said these are just the vapor and liquid compositions of the liquid phase and vapor phase. I was wrong. These are actually the liquid these are the liquid flow rates depending on the section. So depending on your well, this is the liquid flow depending from the rectifying, I mean depending on the composition. I mean depending on the component, so at oh my gosh, I can't talk. How do you say that? So these are the flow rates, respective to each stage, respective to each component, either water or ethanol. Okay. So I'm assuming because since we have ethanol first, we have our ethanol flow rate and our water flow rate, you know, yes. or ethanol and water flow rate. So it's just depending on what we have for our current. I know it does switch depending on the more volatile species and the flow rate, but yeah. So these are flow rates, not compositions. I'm sorry. I just misspoke. But yeah. But yes. Okay, back to sorry, it just popped in my head because I said that wrong earlier. But yes, now that we have this, we have all of our equations. So we can put this into a row. So we do JMP and dot R, and this will be we do mass balance, equilibrium relationship, and then enthalpy balance. Shift enter. What's the problem? Oh yeah. So then for this gas here, we would do the bubble T at oh no, an RTL respect to what composition? No, this is X, I'm pretty sure. And temperature. I forgot what this was. What is it? Is it pressure? Yes, pressure. Oh shoot. I forgot. I forgot. Let me check real quick. So I can show you the answer. That let me show oh my gosh, I can't talk, it's too late. Let me see real quick what this is, so then we can see if we have the um right answers for our equations. So I'll be right back. Okay. Um, yeah, my brain's not braining right now. It's literally just a copy and paste of this. So all we gotta do is literally copy and paste this. But yeah, um, sorry about that. But yeah, I don't know why my computer keeps doing this. It'd be bugging sometimes. There we go. Hit enter. There we go. And yeah, these are right. Because I remember this number here. Yeah. These should be right. Of course, I'm gonna check everything at the end of this section, but yeah, these should be good. Okay, so now let's get to the next stage, which we can just clearly copy and paste this and go work to the next stage, which we will do all the stages in between the condenser, the first stage and before the reboiler. So we'll just call this stage N. Sorry, it was bugging me. And like I said earlier, we will use vector one to represent the stage above the current stage we're in. Then we have our current stage, and then we have the stage below our current stage. Okay. And then we don't need a reflux T anymore because we're not dealing with the reflux, because we're not dealing with the condenser anymore. But we do need our feed because we have to deal with the feed stage. So we have our feed, then the enthalpy of our feed. So that'd be FH. Okay. Now, and then this, well, literally just copy and paste everything. Now just incorporating the new vectors that we have for stage above. So we have L1 and V1, and then that would just be for V1. We have still the same R vector for the current stage. So V and L and V, and then the stages below the current stage. So vec2 for V L2 V2. Then the temperature we will have temperature above our current stage of T1. We'll have temperature current stage T and temperature below our current stage of T2. And this will be equal to now vector vec2 of -1. Of course, still pulling from the last column. Current stage and then last stage. Okay. Composition still stay the same. And then now our mole balance, our mass balance and our enthalpy balance now changes. And then like I said, our the equilibrium relationship does not change. So we are good there. All right, so mass balance. Now we are just dealing with the feed stage kind of. So for the feed stage, we know we have the feed entering. So we have our F entering. Um, yeah, we have F entering. We also have the liquid from the stage above. entering our current stage, plus the vapor from the stage below also entering our current stage, and then also now we can just subtract from the liquid leaving from our current stage and the vapor leaving from our current stage. Okay, and this is also divided by our total flow. Okay, all right. And then now, sorry, mine just blank again. I really need to go to bed soon. Next we will have our enthalpies from our mass balance. So this would be our FH for our feed enthalpy plus our we don't have to need our reflux anymore, but this would be uh liquid above our current stage, respect to T1 plus the vapor. So this everything else is actually the exact same. So then we're good. And this can be shift enter and copy this speed stage in now. And now we also have to add this would be unknown of 2 to be the stage below. So now it's be a stage above, stage below, and then means stage above, current stage, stage below. And then now for our feed, we'll just do our feed tote times our C. So the feed coming in, total feed coming in times the composition of our feed. And then the next part would just be our feed enthalpy. So feed enthalpy. All right. So then enter. This doesn't look right. Yeah, this is not right. This should be like 1.0008 for my reference. I'm pretty sure. So where did we mess up on? Hmm. Okay, so I know for my temperatures, this is also wrong. This should be V1 here. Maybe that should help. It does. Perfect. So yeah, I just had to catch. I actually put vector 2 for both of the references here, so it double counted for our T1 and our T2, and it should be pointing to different temperatures respecting from our columns here. Okay. So yeah, this is now correct now. And now our last part is that we need to grab our reboiler. So let's do our reboiler, and we'll call this um oh, I messed up on my names. This should just be stage for just representing all the stages, and then this should be stage N, respectively. Yes. All right. I don't know why it's taking longer than usual, but let's ignore that for now. There we go. All right. So stage N, this will be representing our reboiler. We don't need stage below, don't need feed or feed enthalpy anymore. We just need the stage above, the stage above in our current stage. So like I said, don't need stage below. There's no stage below. We're at the most lowest stage. Um, don't need this for temperature as well. Everything else is fine. For our mass balance now, this would just be the feed going in. So there's feed coming in from stage above. So L1 minus our liquid leaving and our vapor leaving from the current stage. And then from here for our enthalpy balance, we actually be different. This will actually we'll actually need to do another mass balance here. So this would just be another mass balance instead of another enthalpy balance. And what we'll have here is that we'll just do the JMP sum for our liquid coming up from the stream minus our JMP sum of the liquid at the current stage minus JMP sum of the vapor leaving from the current stage, okay? And then this will all be divided by, no, I'm sorry. So what we have here now is that we have we're doing another mass balance of the sums now of the liquid coming in and the liquid coming in, the bottoms leaving from the reboiler, and the vapor leaving from the Reboiler. Okay. So what we have here is that we have our liquid coming down from the stage above from the reboiler. We have our vapor leaving from the reboiler stage. And then now we also need to add our B tote. Okay. So this would be the bottoms, the bottoms flow leaving. And we have to multiply this by what is this? I don't think you have to multiply by anything. Do we have to multiply by something? Mm, I don't think so. I think we're good. I think we're good. I can check real quick before we do when we check our results. But then we also have to multiply this by F total. Okay. Um, this is now be NB2, NB2. Okay. So shift enter, and then we can check real quick our results. And this will now just be we don't need any of this. But this will be from the stage right before the last stage. So our stage 9, and this can be our final stage. So stage 10. Shift enter. Oh, stage N. I think we're right actually. Oh wow. I'm not gonna lie, I thought this would be off. I truly thought this would be off. I think we're right. Let's go. Let's go. Of course, I'm gonna check the numbers real quick. I'm gonna check the numbers I'm gonna check the numbers when I have my break. But when I pause for shortly before we start the next section. But okay. I think we're good though. I think we're good. So yeah, so now we have all of our stages um kind of defined now. Well, we have derived all of our stages for the stage below, not defining our condenser, of course, but the condenser from the stage below the condenser down. We have derived all of our equations now and have an enthalpy, a mass balance, equal. Oh my gosh, I can't talk. I can't think. A we have our equations. I was gonna say that we have our equations for all of the stages from 1 through 10 respectively. And I think they're all correct as well, which I was kind of shocked I did this all right the first time. So we're very pleased. So next now we have this marked off. We will now get into implementing the Newton's method, which we did up here in part A, and applying Thomas algorithm for the linearized tridiagonal block equation. Okay, so what we kind of do is tridiagonal block equation again and use the variables that we have here for our guesses and kind of work backwards to find our compositions and at the end. But yeah. Um yeah, let's get into that next. Okay, let me check my numbers and then I'll be right back. Okay. To continue where we left off, as you see, it's a new day. I was too tired last night. It was like 3 o'clock in the morning. So I said, let's go to the next day, finish this off. But to continue where we left off, we started our mesh equation. I just go to the rundown. Started our mesh equation calculations from previous work videos we had from dynamic distillation. I think I don't have my reference anymore, but it was from dynamic distillation, our Poisson-Savart. I think there's one more. But to set up our initial information for our mesh calculations, and then we use our initial guesses from equations we have from this regular distillation column, and then we set up a guesser basically. So we used a unknown. So we had an MP0 as matrices from a 10 by 5. So from our columns, knowing that we have 10 stages, I don't even need all this. Okay. So I'm here to continue the rest. As you see, it's a new day. It was too late at night, and I was gonna finish it all out tonight. All right. So remember we left off. We just got done deriving all the equations for all the stages. So the stages below the condenser, the stages in between the condenser. I mean the first stage and the reboiler and the reboiler. Basically, using our unknown matrices uh, that we had, that's the 10 by 5, and then plugging in the information equations to, find our equations. That's kind of like our guesses that we'll plug into our Thomas algorithm for later on to get kind of work our way through this mesh equation. Okay, so now we have our guesses. We have our matrices full of guesses for all the stages, our columns, and then now, so I can print them out here. Actually, we have here. But now, I do want to check, let make sure, there was two things I caught that I needed to change. One, for all my sums, for my low compositions, for each stage, it need to be excuse me, JMP and not just MP, because I remember we're in the Jacobian. We're using Jack's Jacobian, so everything needs to be JMP and not NP for nobody. Yeah. And then the other catch I saw is that I saw that my numbers here for my liquids um were not matching up with the my reference that I have, and I was kind of confused, and I realized it's because of the order that I have for my material balance. I guess this needs to be vapor, then liquid first. I thought they would be the same, but as you see, there's two you get two different answers depending on the order that you have it in, which you got to make sure, I guess, make sure that you have in the correct order if you are writing this down with me. Because I made the mistake and it took me a long time to figure out what the problem was, but then I figured out it's just an order thing. So here we go, have it now. But yeah, now let's get started. So let's move this over here. I also want to open, no, I don't want to group that. I also want to, actually, I should cut this over here. I'm sorry. I want to open up the collaboratory and open up our tridiagonal that we did for part A because we will be needing this a lot for the next part since we're doing the Thomas algorithm. So, or there. So let's get started. So first, kind of like I just said, we are now doing part two, the second part. So we're doing using a new methods and applying Thomas algorithm for linearized triangular block equations. Excuse me. So what we kind of do is we're kind of replicating what we have over here, over into our mesh equations. So we know, and that's why I pulled this up, that we already have basically what we're setting up is that we already have this orientation over here. Okay, so that's where we are trying to now construct now from our unknown matrix that we have filled with our guesses. So we're trying to first now organize our equations. So we know we have our modified E's that we have in our modified C's. Okay, so we know we have we have our modifieds that we have to then, if I go over here, we start off, when we go over here, we had our stages, of course, and then for this case, we had numbers. So we already had values put in for our matrices, but for this case, we don't. We're actually just using our equations instead. So we'll kind of be using our unknowns for applying and then applying the equations to kind of construct our numbers for our matrices. So let's just start. First we do our E. So we will construct our E's first. This will also be a 5 by 10 as well. So we do E's is equal to NP dot, and we can do NP zeros like, because it'll be the same as our unknowns matrix. So like, and this would just use for unknown. And like I just said, if we want to see the shape, this would just be 10 by 5. But yeah. For this, the nice thing about this, we're actually just taking all of these, which is really nice. Okay. Basically, what we want to do is that we kind of want to plug all these, what we have for our matrices for our unknowns into our E's. So what we will do is that we will, for our first stage, of course, all we're doing is just literally taking, so the ES of for our first row. So you want to take the, if I, do I have an unknown? So yeah, we kind of want to just take our numbers and transfer them over. So all the values that we have from what we generated from our equations, we want to just transfer them over into our E matrices. Okay. So what we'll do, take the first row and we'll set this equal to our stage one. And I think that's all we actually have to do. So we evaluate this. Kind of just hard coding all this stuff out for the first part. So, and we look at our ES now, you see that, I don't know why it's like this. I even when I put full screen, it still does this, but now we have our first column filled out and we have the rest that we have to fill out later. But yeah, this is representing our first column. So first stage, okay. Next we want to do all the stages in between the first stage and the reboiler. So we actually need to do a for loop to kind of represent this. So we'll be doing using I. So we for I in range, and we'll be using from our first stage, of course, and then to the last stage right before our reboiler. So NS minus one. Okay. And then for this, we will kind of say that we need to also incorporate when our feed gets incorporated into this mix of stages. So we know our feed comes in at stage 8. So we need to say, so we need to also say that. So we need to say if when our so if our I, so when our for loop goes to the 8th number in our for loop, when it gets equal to the number for our stage, we have to state that our ES for that respective I is equal to stage. Yeah, it's really is equal to this. Okay. And then else, so all the other stages when it's not the feed, we just so when this statement is not correct, 'cause it only happens at one stage for when the feed comes into our equation. We want to kind of just copy paste this, but instead we're not adding a feed anymore. So this would just be zeros. All right. All right, and then lastly, we have our reboiler. So last our reboiler. This one's pretty easy. All we had to do is fill in our E's are at the last column, the last row is be equal to of our staging of our unknown two and our unknowns ones. Okay, so this is kind of literally all the setup we need for this. It's pretty simple. So then we do shift entry. We do our E's. I forgot to colon. So now we have equation for all of our E's now. Perfect. All right. Um, Later on, we do need to evaluate our equations. So from our equations that we have, so our ES is, like I said, represents our equations that we have from up here. So we do later on when we put all this stuff in for our modified information, then we come down to when we try to find our X's or our deltas for this case. We would then need to evaluate our equations again so we need to evaluate our equations. So evaluate our equations, and then we will have to, what is it called? I think, what is it? Modify. Oh, we have to evaluate our equations. So then we need a function for this. So that's what I'm trying to get at. That we need this will all be in a function later on for evaluating, right? Evaluating our equations, respect to our unknown. Okay. So I'm gonna just turn on. Actually, I can't do that right now. Okay. And then we'll return, of course, our e's, I mean, our equations. Let's back to this. And then we'll also have a function later when we do run our last part, our integers for calculating our delta x's for our equations. We also need to normalize our equations as well. So we have a function for normalizing our equations at the end as well, which we'll get to later. Oh my gosh, I can't spell. Oh my, okay, there we go. And then this, I think we return is JMP linear algebra dot norm of our evals at ES of our unknowns. Okay. All right. I'm just doing this now. I'll explain, of course, more when we get to these later. But I just want to put these now so I have them. Just so I don't have to write them later. I just have them now. But yeah, it's kind of all we have to do for this for our E's. But now let's get to our C's. So we have to get to now. We have to do our modified C's. Okay, so this one stuff gets kind of tricky. Not gonna lie. Yeah. So our modified C's are a little bit different. So for this is why we actually have a block um tridiagonal matrices, not just regular tridiagonal matrices. Because now for our C modified. So let me pull this up. For our variables A, B, C's, so let me put our C modifies. We kind of, oh, wrong one. C mods, C mod. So when of course, this would be a matrix C as well. So it'd be NP zeros. Before this, um, we would not have a regular 10 by 5. We actually have a 10 by 5 by 5. And this is because all of our variables here, so our B's, our C's, our A, B's, and C's in our matrix C here are actually 5 by 5. So they're their own 5 by 5 matrices. So every single thing, so basically in our equation, we kind of have for our first part is 5 by 5 times our X here, times our X matrix C is then equal to our equations. Okay. So that's why it's a block diagram, a block tridiagonal this time, not just regular tridiagonal, because we have a 5 by 5 times another series is equal to our equations this time. So yeah, it's kind of more compact into a block. Block by block. But anyways, yeah. So our shape for this, like I said, it'd be a 10 by 5 by 5. So how we do this, we just of course do our number of stages. Then we'll do kind of what we did. Or did we do this up here earlier? Um, I'm pretty sure we did. Yeah, we did. We did our unknown matrices. Um, but we'll do it two times our number of combinations plus one to get our five, and then we'll just do the same thing again. So sorry, kind of blank. And then if we do a shape, just to see the shape, make sure it's okay. Hit enter. Oh, I can always do this. Even when I practice, I delete this every time. Oh, I didn't do that, but do double parentheses for this. And then you see now we have a shape of 10 by 5 by 5. Okay. So now let's get started. Okay. So we kind of do the same thing we did up here a little bit. But the only thing is now we're using our modified. So of course, we have for our first row, we have modified B's and C's. Then for our first stages, so for our first stage, we'll have a modified B and a modified C. Um, and then for the stages in between our reboiler in the first stage, we'll have A, B, and C, all those variables modified. And then our last stage, we'll have A and B, which will be modified as well, which we did actually all here. So I'm just going to kind of copy and paste this and then adjust this as we go. So for our first stage, And again, like I said, we got to kind of hard code everything for right now. Um, Actually, do I even need this part? Oh, I almost got the main thing. Okay, so for this though, we do need to put our stages that we have up here in a Jack's Jacobian. But we'll in a Jack's Jacobian. Okay, so what we need to do. Oh, I almost forgot. That would have been a huge mess up. So we need to copy and paste all of these. Well, I'll do the first stage, but we'll put these in the Jacobian and we'll Jack's this too. Which Jack's if you forget, just makes our running this function faster. Which is very important because this is a lot to run in Python. So Jack's getting it makes it faster, so it doesn't take that much time. So Jack's Jacobian, okay, and then we would put the stage one, and then we will only for this we need to put parentheses in here. We will only be taking the variables, so the vectors in here. So we're gonna count this as 0 and 1. We don't have to worry about our temperatures or enthalpies for, the stages of blah, blah, blah. We just need to worry about the vectors. And we were captured this by just 0 and 1. So we will have two vectors. So 0 and 1. We can copy paste this for all of them. And we just got to make sure to change everything respectively. So this should be just the stages. Should be stages. And then we have three vectors. So 0, 1, 0, 1, and 2. And then this would be stage N for reboiler. Okay, and then this is the exact same. Okay, so shift enter. Perfect. All right, now let's get to the tridiagonal stuff. Okay, so I want to start this, Evan. Um, yeah, we can just copy and paste this first. Yeah, we can go for it. Let's just go for it. Um, like Jay says, just go for it. Works out for him. Let's see if it works out for me. So, yeah. For this, kind of like I said earlier, they already had values for they already had values for um what I'm trying to say here. They already had values for the matrices up here, but we have just evaluating equations. So what we would need to do actually is that so for our CMOD at the first column, we will say that at stage one, at the Jacks, as a Jacobian, and all we have to do is now import our equations to pull our equations from up here. Okay. And then we also do the same thing for our ESs as well. So our ESs, our equations at the initial is equal to, these copy and paste this as well. Stage of the Jacobian. All right. So this is actually the first, I think, yeah, this is actually all it is for the first one. I was overthinking it. Yeah, for the first one is all we have to do. So we have to just import the Jacobian now, and then it'll be now our return. So our equations will now be evaluated in the Jacobian region. So it will give us a new answer. So if we should enter this, should work. Not setting an array. Oh Lord, what do we do now? What's the problem? It should be fine. Let me make sure this is correct. Well, actually not correct, but what's the problem here? Pretty sure this is right. Let's make sure this is. I'm gonna make sure what the problem is, and I'll be right back. Okay, I'm sorry. I'm totally wrong. I was thinking something else. So let's restart over. So now we are now getting our modified B and C. So now we had to start with our B and C up here. So our first column, so we had to plot out B and C. It kind of tripped me up because usually for the other ones we actually had A, B, and C represented. So I'll just go down like that. But first, because like I said, this already was printed out. We just captured and grabbed what we had up here. But here we have to, like I said, since we are using our equation matrices for our B and C's, we have to kind of capture this from our first row that we have um for our E's and our C mod matrices. So what we will do is I will say that our B and C's are equal to our stage one. This is what I was trying to do. Our Jacobian, and then we will plug in our unknowns. Yes, and then that works. Yes, okay. So from here we can now determine our B and C variables in our matrices. Remember these B and C's are 5 by 5 matrices themselves. So that's why we have them capital instead of lowercase. Um, but next we need to, of course, we know that our C mod at the initial gets divided by our B. But our B is, for in this case, since it's a 5 by 5 matrix, it needs to be an inverse of B. So what we would do now is that we would say that our B inverse is that we say that we need to do inverse of B, like I said. So we do a JMP, linear algebra, inverse of our B matrix. Okay. And then from this, we can now use our B inverse matrix C to now find our modified C. So this would be B inverse times matrix multiplication of C. Okay. Oh, excuse me. So now this is our new C mod now. Okay. At the first column, of course. And then for our equations, our E mod, ES 0, this will be equal to and this is what? Our B inverse matrix multiplication of just our equations that we already have up above at 0. Okay, so now this is our new uh this is now our new column new row for our equation matrices. Okay. So now we have our first column here and here. Okay. Next, we want to get the rest of our columns here for our equations. So we want the 1 through 9 equations, 1 through 9 rows for our stages. So we would now use this here for our tridiagonal. So I'm gonna copy paste this, comma, pound all this out. So kind of leave them as references for me to go by. Um, So we're actually still be using a for loop, but the range will now be from n, it'll be from NS's. So now this is just saying that from 1, so from our first stage, all the way to the stage before the last column. So from 1 to 9, which we're actually looking for. So this works perfectly for us for our for loop. And we actually also need in our for loop, is this also this other for loop, no, not this if and else statement for our feed. Because again, we are incorporating feed into our column, and we need to figure we need what the heck? Oh, I forgot the if. I've got the copy and paste if. But we need to make sure we know when the feed is coming into the column as well. So we need to incorporate this if else statement in for this modified matrices as well. Okay, so everything is kind of copy and paste as well. Um Stage, and this is the Jacobian now. Jacobian, everything inside here stays the same. Um Our ES is at I. Yeah, these are all stay the same as well. Nothing changes. Oh, besides this, so we need to state that this will be now I before our current stage. So this will be the before our current stage. I representing our current stage, and then I after our current stage. So I represents our current stage, so then it'd be the stage before our current stage, and then the stages after our current stage. Okay. We gotta do this here as well. On this one, this would be I, this would be I plus one. All right. Okay. And then from here, we will now change our ESIs. So we've changed our equations because we're not trying to find our equations here. We're trying to find A, B, and C. So we're trying to find our A, B, and C variables from this. So instead of our equations respect to the stage, we're gonna do our A, B, and C matrices respect to the stages. Okay. So we'll just copy and paste this. Uh, Okay. Yeah, okay. All right. Okay. I don't know what happened. All right. And then actually this I can just delete this. Actually, I'm gonna move this up here to know the references. Okay. Next we also want to do the same thing. So we know we have our modified B and we get to also capture our modified C's and our modified equations, so our modified E's. Okay. So for our modified B's, we gotta do the same thing we kind of did up here. We gotta do the inverse of our B's. So which we can say our B modified, because it's still also modified, but the inverse now. And this will be equal to JMP linear algebra dot inverse. This would be of B. We also put the rest of the equation as well. So our B minus A times C modification at I minus 1. So we'll do B minus A multi at the matrix multiplication of our C mod at the stage before our current stage. And then this needs to be also in the for loop, which I think it is. Is it not? It's, maybe that'll help. Let me just, well, it's not, it shouldn't be in that loop. There we go. Next we have our C mod. So our C mod at I, so at the respective stage is equal to our B mod inverse at matrix multiplication of our C. Okay. And then lastly, we have our E mod. So we have our equations at respective I. And now this will be equal to, again, kind of like we did up here, but it'll be our B mod inverse at, and then this will be at ES, respect to the stage, minus our A, matrix modification or C mod modification, C mod at the stage before our current stage. Okay. So this is now, this should work now. Cannot input a 5x5. Um, it should be fine. 5x5 to the 5x0. What's the 5x0? Talking about this? Maybe. Hmm. I might get to the next part and then maybe we'll come to the last part. That's kind of okay. Anyways, the last part is our A's here. So now we're just be using our A, B, so we're capturing our last column. So where we just have A and B variables. So kind of what we did up here, same case, have A and B is equal to stage and the Jacobian. And then this would be from our unknown for our equations. Um, yeah. Our B mod So of course, like our previous, we have be the inverse. Oh my gosh, there you go. P inverse, this is equal to JMP. Linear algebra, not inverse of RB minus RA times RC. Oh no, extra multiplication of RC mod at the stage before. So it'll be NS minus 2. So it's the stage before our reboiler. Okay. And then this is this should be the exact same as this. So copy and paste. Now for our E's, remember we don't have a C here. C is not in our last column, just A and B. So then for our E's, which we know our E is equal to our X, our last X. In this case, it'd be delta. But be our E at the last row is equal to our B mod inverse at our ES at NS minus 1 at NS minus 2. Shift enter. And I'm gonna check real quick because I really don't understand what the problem is for this one. I think this is right. I'm gonna check real quick. And I'll be right back. Okay. Small mistake. I just didn't catch this, but it even says wrong reference. But it's not our modification at C. It's our E's. So it's our it's our equations at the stage before our current stage. So this is our ES. So we need it for both of these. Capital E, capital E, and then shift enter. Now we have it. And then if we want to now check our E's and our C modification, we can. Oh, these do not look right at all. What the heck? Oh yeah, I forgot to. So for this, it kind of starts with our first row, but we are actually pulling our vapor composition. And we need to kind of pull this from our new ease. Now we can't pull it from up here from our stages. So we need to actually capture this in our func in our equations down here and not up here. So I'm just going to copy and paste. I'll put it right here. I forgot we had to do that. Um, that should make a difference. Um, okay, shift enter. Oh yeah, it's unknowns now instead of our vectors because we're not in the functions. Always be 0 too. I also gotta add 0. There we go. All right. There we go. So these are still not right. They're still too big. Oh, I'm in the wrong. Okay. We have that we run our modify and get our new equations. Perfect. Yeah, so now we have now because our equations, I mean our values that we got we were way too big and they didn't be close to 0. These definitely work. They're all close to 0. I'm gonna check it for my reference to make sure that this is what I got from when I was doing my practice run. But this looks good, and we can also check our C mod. So what that matrix C looks like. So our 10 by 5 by 5. I'm gonna full this one out. But yeah, as you see, we have it goes to our last 3 rows are filled out, which that's exactly what we're looking for. So yeah, um, he got that filled out. Okay. Our excuse me, our last row is not filled out, but I think it should goes as no, it should be filled out. I'm gonna check if it should be filled out or not. I'm not sure. We do have our uh numbers filled out for RC mod as well. I'm gonna check all these numbers before we get to our next part of the Thomas algorithm where we go and now we have to use our X we have our delta values now to kind of start using for our to evaluate our equations. So we're working backwards now. So we're going to use our modified equations and then evaluate them to then plug into our x's here, where we go do run it for a certain amount of integers to see what our values will be for our roots. Okay, so I'll be right back. Okay, to continue where we left off, we were just now derived the kind of the Thomas algorithm. The basic, no, we derived the base of the Thomas algorithm. So we have our regular e's, I mean regular equations that we have from up here that are not modified yet, which we use to then find our modified e's from using our modified C's and capturing the B through C's for the first column, A through A, B, C variables for our modifications. And now, so we have the base. We have our modified A, B, and C's and our E's now. And then now what we want to do is that we want to now, sorry, we want to now use this to basically find, let me save this. My computer crashed earlier, so that's why it's saying like saved failed. But it's fine. Save your names. Um, but basically we want to now use, so go back to try diagonal HC that we had earlier. Use our root solver now. So this bad boy right here, to help us solve for this. So basically we need to now make our root solver now. Okay. So what this is, I keep mentioning, but I think I keep phrasing it wrong. We are trying to find our root scalar. We're trying to basically find the roots. In this case, for us though, my video not showing. Is it? There we go. Sorry, it wasn't working. I wanted to make sure. Um, in this case, it will be our delta unknowns. So our delta unknowns in this case will be our our roots in this case that we're trying to solve for. Since it's a block diagonal, we're trying to solve for matrices. Um, but yeah, we are trying to solve for our delta unknown. So instead of our x's, which these x's represent our guesses. Okay, so we're trying to find our guesses here, which is a 5 by 10 matrix. There it is. All right, so now, so delta known. This is now you can really just kind of copy and paste what this is really is basically. So we empty the zeros and we can do like because it'd be the same 5 by 10 as our other unknown metric matrix. We know the delta unknown, the last one is equal to our last modified equations. That's just ES -1, and this is also -1. We still have this for loop, so for I and range. Remember this for loop helped us. So we started right before the reboiler, and then we kind of worked our way up. So I can kind of show that real quick. I'm gonna do print I. Missing. See, look, so we started at 8, and we go all the way to 0. So yeah, that's what we want. Oh, not my that remind me. Okay, so there were some changes that I found that we need to fix before we keep continuing. So we'll start from all the way up here from the top. First, when I did our sections in between the condenser and reboiler, I forgot to incorporate the I for the changing for the different stages. So for the stages above the current stage we're on, the current stage and the stages below. I forgot. I just used 0, 1, and 2 instead of actually using our I since we're in the for loop. So I need to do that for this. There's a few mistakes that I caught that I need to fix because it affects us definitely at the end. We can shift this for that. Yes. So our C modification, this will affect our last set as well, but it needs to be a 9 by 5 by 5, not a 10 by 5 by 5. And the reason it is because we're not including our condenser in this case. Our first column actually is first, of course, the column above the condenser. So we're not incorporating that condensing column because that's where we're not using that. Well, we're using the condenser, but we're not modifying that. Okay, so it needs to be -1. We're not, yeah. Okay. So what else? Um, yes, this needs to be changed to 2. I think I messed up on my tridiagonal matrix, which I thought that was correct. I'm pretty sure. I mean, it still worked out fine because we did the video and it worked out. But it's supposed to be -1, which is yeah, I forgot to change as well. Yeah, so these two last I forgot to change back, but this is supposed to be -1. I had a -2, and then these I had it as the NS. So the stages, and then I just subtracted from what we have for the stages. Um, we don't have to do that. We could just, keep it as -1. That's what I have for my reference sheet. Um, I don't think it changes that much. I think it's the exact same actually, but I just want to be as close as possible to the reference sheet because I've practiced multiple times and the littlest amount of difference that you have, it'll mess up the your equation, like your code so much. So at the end, so I'm just trying to be as close as possible to what we already have. Okay, so now back to this. Like I said, we're back to our deltas, and then we can just fill this one in. So we have delta unknown of I is equal to res of I minus our C mod of I at our current stage. Matrix multiplication of delta unknown at the stage above the one we are currently in. Okay. Shift enter. And now we have basically our root solver. So technically we would be done. In the tridiagonal, we would be done. And basically what this is doing that we are basically finding our roots from using the unknowns we have, so the guesses that we originally had, and taking this and adding this from the delta unknowns that we are capturing from the modified equations. And this should theoretically equal to 0. But we find out that the delta unknowns are actually not exactly don't actually correlate exactly to the unknowns to get a 0. There's some slight differences that take place in delta unknowns using because we reference our un well, it's because we reference our unknowns with the block tridiagonal, and by using our unknowns, it like made it so the delta unknowns really doesn't exactly correlate to the unknowns that we need to get our roots basically. Hopefully I said that right. But well, we do need that, but because of this we need to add a factor, so a factorial multiplication for our delta unknowns to get us so our unknowns are equal to 0. So we need a factor of t, and t is what we'll be using for basically a multiplier factor to help us reach 0. And for this, we'll use two things, minimize scalar and bracket. I'm pretty sure we used these before, but we'll be minimizing the scalar of this equation to help us basically to help us literally find our roots. And for this, we'll actually go back up here. We will be using evaluated e's and normalized normalized e's, normalized evaluated e's. So yes, we finally are using the functions that we put in the way beginning. Okay. And what these do is that we're basically using our evaluate e. So we're using the function for evaluate e's that we had earlier. And from this, we will use our evaluate e's. This will be normalized. And then from our normalized evaluate e's, we will, of course, run this through our functions that we're about to print out, which will basically kind of like working backwards. So so we're going to capture our evaluate e's, and we'll run through our matrix here, and then it'll go back up to our normalized evaluate e's where it'll be normalized, and then we will run it through our do our inverse to basically find our roots. Well, we have our two functions to basically find roots, and then we use this, and basically we'll find our unknown roots. That didn't really make sense. I know it kind of didn't, but we'll work through it and hopefully it makes more sense. But yeah, we're basically using our evaluate e's Use our evaluate ease. From our evaluate ease, run it through our code. Then our code will get our modified ease. Then we'll normalize our modified evaluated ease, and then we run it through our solver. Okay. So let's get started with that. Um, we'll need to keep this, but I'm gonna copy this because this would be the basis. And I'm actually let me delete this. I'm gonna combine these, all these. So like I said, we need to use a minimize scalar, and we'll be using a lambda function. So for this, we need a function and a bracket. So our function we'll be using is a lambda. Before the lambda, we'll be importing our normalized evals function. And then inside the normalized evals function, we're using this equation right here. Okay. And then we also need this for the bracket as well. So the bracket that we have here, that then we need to either have a triple tuplet for, we need to also have a function for our bracket. So bracket, we call bracket is equal to bracket. And we can actually just copy and paste this. And what we need to do is that we actually need to take these, so we need to pull these for our set points for our brackets for this to run. XA0, it doesn't work, even though it should already, because it's optional, so it already should be in it, but it doesn't do that. So we need to actually just state that. And then from here, we're actually grabbing I mean, I can show this real quick, but shift enter. Why is it not running? Not me. Let what I had actually then. Right. For a bracket, we'll be grabbing. I hope this was like, I was wishing this was more like visible, but we'll be grabbing these 3 points here, and this would be our range for our bracket that we need for our minimized scalar. So what we'll do here is that we'll do new bracket. And then what we do is that we're to grab everything into the fourth number. So, sorry, that was my mom's phone. I'm in her office again. But we'll be grabbing all three of these numbers. We're not grabbing the fourth number. So we're grabbing all, oh no, we're not grabbing this 233, but we're grabbing the numbers right before the fourth number. All right, so we get everything to the third one. And this will be our T value actually. All right. So I think we have everything actually now. Shift enter. Does work. It's not yawning. That's important. Oh yeah, this is equal to our new unknowns that we're finding. Yes, equal to our new unknowns we're finding. Oh, okay. So it's doing this because so our next part that we need to do is that we're doing an iteration now. So we're doing an iteration. So now we're doing this is literally our last part. So we're doing an iteration, basically to find how many times it will run for us to finally solve this to solve for our roots to get a root. So what we do is that we'll do for enter in range of 1 to 25. We'll use our ease, so our ease that we have, ease, and this is equal to our evals, es to unknowns. We have our modified ease, so our normalized ease. is equal to our normalized evals function for our ES, our guesses. And then we will print these out. We'll print the iterations and the normalized E's. And then if our normalized E's, we need to add a break clause, kind of like we did for the try diagonal up here. I don't know where we did this. We did add a break clause. I don't think I finished this one, but we did add a break clause. I don't know. I think this is my practice one I worked on, but there was you do had a break. I don't know why we didn't. Okay, anyways. But yeah, actually, I don't think it was there, but we did it anyways. But we need to have a break so it stops iterations. We definitely did it for that. I don't know where. I think I put it the wrong tridiagonal I have, but we for our normalized ease. Once it gets to a certain point, uh, we need to have the iterations break. So we did in class 1e to -8. Okay, and then that's where it should break. And then from here, um. From here, oh wow, I just realized I already printed this out earlier. I forgot to add this. I didn't even peep that. I'm gonna just keep it, even though I didn't even notice I had that because it was commented out. That's why I kept it. I'm just keep it for now. I have to re-record this. I record this. But, um, from this we just have to now shift this all the way over, shift everything over, so it fits into our for loop. Um, should be good now. No. Where's our norm? I mean, yeah, we're making a variable, so yeah, this should be fine. What's what's happening? I'm just in the problem here. Let's just run it and see. And I don't know why it's highlighted. This should be fine. Unexpected indent. We're in the for loop. What's the problem? Oh, it's because I have this here. I'm like, what's the problem? Okay, now let's rerun this. Okay, everything should be good now. And we should now see how many times our iteration will run for and what our roots will be. And we'll also graph out ES to see where our E's are. Oh no, what's the problem? It's still not. What? What's wrong with this line? I'm gonna check real quick and I'll be right back. Okay, so I forgot my mistake. I forgot to incorporate a return for the function for the evaluated ease. So it wasn't actually grabbing anything. That's why I was kept highlighting an error. I totally forgot about that. So yeah, our ease really was doing nothing. So when we do our normalized ease down here, using our evaluated ease from up here, excuse me, nothing was getting caught. So that's why I was kept shipping up an error. I was wondering what was wrong. Now, if we run this again, this should work. Um, hopefully. I pray this works. I pray this works. Please work. Yes, yes, it's working. Okay, the first number is right. Please be zero, like 0.00 something. Um, okay, I want to make sure that nothing was like glitching. Please, it's taking a long time, which I don't like. That's right. That's right. Okay. Thank God. Okay. So yes, we have now our solver. So we finally finished up. Yeah, we got it. Okay. So this should run for 5 iterations. Um, and we can also print out our E's to see what that looks like. Get our new E's. Actually, it doesn't matter. Yeah, we have our iterations. So yeah, I don't think our E's will change. Um, that's all accomplished now. Okay, so now we finally finished part two. We have our iterations. We got our solver to work. Took 5 iterations, but we got our roots now, which is around 1.17 for our functions. And then if we graph unknowns, oh, not that. So what our unknowns will look like. Um, they're pretty high. Not gonna lie, they're pretty high. They are pretty large. I don't think they should be as large. We will check when we plot these out because now the last part is just plotting out. So I'm gonna plot these out and then we'll figure out what the problem is. Okay. But I think I'm gonna check real quick. I mean, I know our direction is right, which is great. Like if I run all again, it'll work this time. I don't know. This is very sensitive, like extremely sensitive. Yeah, we have to run basically running it all. It's the only way this thing works. You can't just shift enter and change something shift enter. But yeah, maybe this is very sensitive. So, but now the next part, we need to generate our XY diagram, which is the easy part of all this. So yay. What we're doing is doing McCab-T Um, that's pretty much it. I just want to make sure and check our unknown. Make sure she looks right. They should be close to zero, I thought. I'm pretty sure they should be close to zero, our unknowns. They're not. I'm gonna check this. I'm gonna check this, come back, and we can plot out the rest. We can plot out the McCab-T. Okay. Okay, so now, um, finally at the last part, I'm just plotting out our McCab-Tilly plot. Okay, we finally made it. I'm gonna get this done as fast as possible because it's been already been a long, tiring video. So what we want to do first is we need to now first get our equilibrium curve. We actually be taking our equilibrium curve from our Pontos average from earlier. So we're just taking our equilibrium curve respect to our bubble NRTL to kind of get our equilibrium line for our McCab-Tilly. Then we also need to have our stages. So we need to unpack our stages from our X and Y compositions, which we will be taking from just we'll be taking from this bad boy up here. So we're just using our liquid and vapor that we already have for respect to our current stage. And we're just unpacking our X's here. So we're using all of these, we're taking all of these all the rows all the rows and then all the columns until the last point. So we're not adding, we're leaving out the last column, but we're taking all of these and then some packing and getting the liquid composition and the vapor composition. So what we're doing, first we want to do something different. So I can plot this out to see what we will have for you. What we'll have. So we don't want from zero. We want to take all the rows and then all the columns expect to the last one. What we will get. These are all, let me, here. So we get, like I said, we get all the rows, and every single column besides the last column. And here's all the values that we have. What we want to do is want to split this in half. So we want to have it in a, we want to have it in a row. Kind of, was it? It'll be like a 1, 2, 3, 4, 5. It'll be a 2 by 10. I mean, a 10 by 2. I hope that's right. But yeah, so we want to do is kind of split this in half. Split the columns in half. I mean, yeah, split the columns in half. So what we'll do something called implement axis, and we'll split into one. So we'll do one split of the axis right down the middle. Hopefully this works. Oh my gosh, I keep messing up. Hopefully this works. Yeah. So literally what I said. We're really displaying. We're taking everything. all the columns. I'm just splitting it in half. Um, yeah. And now we're doing it for the X combinations as well. What we want to do now is that we can do these for the X's and our Y combinations as well. So, um, copy paste. So for our X this is equal to our liquid divided by JMP sum for our liquid. And now inside here we will add our axis as well. And this will be equal to 1, like we did up here. But we also, from doing this, we changed the matrice form from our composition. So we also need to rebroadcast our matrices for our X and Y compositions. So what we have to do is we do the broadcasting method that we learned earlier. So we do our colon and then we do none. Okay, and now this should work. So enter for our X, for our Y, not U, our Y. And yeah, so now we have two columns. We have one column, one for the X, one for Y, split down into two pairs. Okay. Next we want to make these into a row. So what we would do now, we'll make our X and Y into a row. So we'll just do X, Y, and this is equal to np.array, nb.r, because we're doing np.r, and we do it for the X, and we will take, what is it? We'll take everything, all the rows. Yeah, we'll just take everything. Yeah. I think we're grabbing everything. I think that's how you put it. Yeah. Then for Y, I'm gonna check real quick. I'm gonna check after this, but I think this is right. Oh, hmm. I remember what we had here. Is it one? Is it to one? No, I'm pretty sure it's to zero, but why did I forget? Basically want to just compact this to a list. So we're taking all the rows and and then we're just taking the first columns. The first column. So we're taking all the rows. So that's where we have this, and then we're taking the first column only for the X and Y. I thought this would work. I'm pretty sure it should work actually. Uh, Let me check real quick. But, I got ahead of myself again. I was thinking of the next step we have to do when you need to do np.r to put them in a row. All we have to do is just state that we want our X's. Uh, you want to just grab our first X's and Y's. You don't have to put it into a row. So if we do that, our new X's and Y's. See, now it says one dimensional though. Okay, so I just messed up. I was thinking too far ahead. We don't need an NPR. I was thinking my next step I have to do, but all we have to do is just state that the X and the Y's will we're just grabbing the first column. And I think I have to also rerun this as well. Um, but this should now just give us the first columns for the X and Y compositions instead of grabbing both the columns that we need. Now we have. So let's just grabbing the first column we need. And then the next step we'll use the NPR linear we have to repeat. So basically we've done this before in McCab and I think the Poncho Cybrid as well. And like other ones we did, but we now have to we're need to double our data points for our McCab plot. So what we need to do is that we have to double our we have 10 data points right now for our X and Y, but we need to double them. So we need to double our X. So we need to double the first. Um, the first, what is it? We need to capture the first data point, double the middle, and then capture the last data point for our X composition. So yes. So now this works. But now like I said, we have to double it. So we need to double all the middle of our X composition. So what we'll be doing is that we're just doubling, we're capturing the first data point, doubling the middle, and then capturing the last data point. We're not doubling the beginning or the end. And then for our Y composition, we're just doubling. We're not capturing the first data point, but we're doubling from the first stage all the way to the last stage. And this should give us what we want for our calculate. We did this in the previous videos, but let's get to it. So for our X, we have np.r. Now we use np.r. And this will be we'll be capturing the first, we're using our Y in this case. I don't know why, but we did in our reference, so I'm just having that what we did in our reference. Then we would do np.repeat. So this will be the repeat that we need to double our data points. And then we'll be taking everything until the last data point, so -1. And this would be from 2. I think it's not, yeah, it's this. Okay. And then, well, this actually needs its own. Okay. And then we need to take a capture the last data point as well. So then we would just do X of -1. All right. And this should work now. Too many one. I may have to run it again. Yeah, it does this a lot. I have to rerun it a lot. Um, oh, I think because I did double brackets inside our Y, which I don't think we don't need to do that. We can just single that out. So I'm gonna wait till it's done running, and then we can delete that. Maybe that's the reason why. Um, where is it at? This one here. Oh, that's why it's taking so long. It's doing the iteration. I forgot it has to do that every time. And these are not fast running. I wish it was faster. I know there's ways to make it faster, but I am not that skilled for yet in Python to do all that. So I'm gonna just let it run. There we go. Yeah, I think it has to do with this. Let's see if that worked. No, it didn't work. Is it because this also has to be bracketed off as well? I'm gonna check again on this as well. I don't know why. I thought this should work. Yeah, this should work. Yeah, this should work. I'm gonna check. I'll be right back. I don't even know what the problem was. I switched this back to parentheses because it was supposed to be in parentheses in the first place, but I just these deconnected and reran the runtime and it worked again. So I'll just leave it like that. But for a while, we're kind of doing the same thing. Um, but for here, kind of like I said, we don't need the first. We're not capturing the first line of code. All we need, and this is a pretty simple one. You don't have to state the differences when we stop. We're redoubling everything from the first stage all the way down, which includes the reboiler as well. So it doesn't, need to state that we're capturing reboiler as well. So and all this is, we don't need to do this. It will just be this line of code, and this should work. Yep. So we have our X's, we have our Y's. Yep. Perfect. And we can kind of, well, that's like too many. Let me do the shape. 160 and 80. That's not right. Should be 20. So let's do this. I do it. I call this XDs. So I know I'm grabbing the right one. 320. Why is it why is it doing this? I don't know. We should only have 20 points. I don't know why it's 160 points. And they should be the same. What is happening? I have no clue why this my code is just like not working anymore. I'm gonna delete runtime again and then rerun everything. Maybe that will work. I don't know. I keep having problems. And it's like there shouldn't be problems with this anymore. But the next thing we'll do, I'll just say it now. We'll be grabbing this, like I said earlier, we're grabbing this for our equilibrium curve, and then we can plot our curve out. So this is the last step, truly last step. Once we have this, we have our steps, say steps that we need for our McCab-Thiele, and then we can then just make up a subplot. I'm just copy this now while we're waiting, so I can just get straight into it. So to make subplots as well. Make subplots. Yeah. See, look, I don't know what's happening. It keeps switching every time. I say it's a really sensitive code. The smallest changes like explodes everything. So, but yeah, now we have our 20 points. Perfect. We have our equilibrium curve line now. So now let's just plot this out. So fit that makes up lots. Fit that add. So we do our equilibrium curve first. And this would just be x is equal to x1s, and then y is equal to y1s. We have fig dot add scatter x is equal to xd's, our data points, and then y is equal to yd's, our y data points. Okay. And we also do a fig dot update layout, at least for our last one. Stay true to what we've been doing this whole time. So we have x-axis equal to, we do 600, y-axis, oh no, height width, the height is equal to 600, width equal to 600, template, the trusty old plotly dark. And we shift enter. X1s. What are you talking about? X1s is not, it's literally from up here. There we go. All right. Oh, let's see what's happening. Okay. Well, yeah, here's our plot. Yes, we finally got our plot. We represent all the 10 stages we have. And yeah, this is our McCab-Thiele plot. We finally got the homework done. Yes. But yeah, here's our McCab-Thiele law. Here's our equilibrium curve. Um, it's not, this is not like a regular curve that we have for, we usually have just a regular a bow. It's kind of like see a curve. I think it's because of the Jacobi. But yeah, here's our lines, data points, our steps. Yeah. And that's it, ladies and gents. That's the last. That's it. RB's finished. Um, hopefully you learned and hope you enjoyed the adventure we just went on. to figure this out. But yeah. Thanks for watching. See you.